Okay, hi, so welcome to the video on the June 2014 physics paper. So this is for AQA Science and this is Unit 1 Physics. This is the higher paper. If you're doing the foundation paper, then some of this will not apply to you. But what we're going to do in this paper, as usual, is go through every question one by one. So if I'm going too fast or there's something that you don't quite understand, please feel free to pause and rewind the video as you wish. So let's jump straight in with question 1. Now, question 1 says, electricity can be generated using various energy sources. Now, we know that's true. Give one advantage and one disadvantage of using nuclear power stations rather than gas-fired power stations to generate electricity. Okay, and now the main one with this, gas-fired especially, whenever you see gas-fired power station, think very quick startup, because gas-fired power stations can be switched on literally within a matter of minutes, whereas nuclear power stations, they take days to start up. So if you need power very quickly, sort of maybe there's a spike, let's say around the 7 p.m, 8 p.m. mark, normally, obviously homes are starting to put their ovens on, they're starting to put their heating on when they get home from work or from school. That's when you see a spike in energy, and you can feel that excess energy need by using gas-fired power stations, because you can just quickly supply more energy and then turn them off. Whereas with nuclear energy, it takes ages to put them on, so they're not suitable for short-term demands. Okay, so that's going to be a disadvantage straight away. A disadvantage is slow start up of station. Alright, now what's an advantage of nuclear power? Well, there are many advantages. One of the main ones is the fact that it doesn't give off CO2. So, very little CO2 given off. In fact, nuclear power itself gives off no CO2, but the power station itself is going to give. But the power station, given that it's not only nuclear power that's being generated, there are going to be other things like lights and that in the power station. It's going to give off a tiny amount of CO2, so that's why I've said very little. Okay, next question, part B. A single wind turbine has a maximum power output of 2 million watts. The wind turbine operated continuously at maximum power for 6 hours. Calculate the energy output in kilowatt hours of the wind turbine. Use the correct equation from the physics equation sheet. Okay, now if you look at your equation sheet, you will know that energy is equal to power times time. Okay? On the flip side, power is therefore equal to energy over time, right? What we're using is this one here. Now, what's important in these equations is you make sure that the units are correct. So energy, we want in kilowatt hours. So what we want to do is we want to times kilowatts by hours. It tells us here that we want kilowatt hours. So what we need to do is we need to have a power in kilowatts and a time in hours. So energy is going to be equal to power, which is 2 million, times by hours, which is 6. Now, that's not quite correct because 2 million is in watts, right? We want kilowatts. So 1 kilowatt is equal to 1,000 watts. So what I need to do is I need to divide 2 million by 1,000. If I divide that by 1,000, I get 2,000. Okay, you just take 3 zeros off. So 2,000 times 6 is going to be my energy output, and that is going to give me a grand total of 12,000 kilowatt hours. So in here I'm going to write 12,000. Alright, moving on. Why, on average, do wind turbines operate at maximum power output for only 30% of the time? Well, this is a 1-mark question and it's quite obvious. Wind turbines rely on the wind. The wind is not constant, it varies. So, wind is unreliable. Amount of wind will vary. Alright, part C. An onshore wind farm is made up of many individual turbines. They are connected to the national grid using underground power cables. Give one advantage of using underground power rather than overhead power cables. Alright, there are a fair few things we can say here, but this is only a 1 mark question. We only need 1 point. So the obvious advantage is you can't see them when they're underground. So cannot, oh, bad writing there, cannot be seen. Right, and just to make sure they know what I'm talking about, I'm going to say no visual pollution. Right, if you just said they cannot be seen, that is absolutely fine. There are many others. For example, they are a hazard to wildlife, overhead power cables that is. Birds, migrating birds fly into them, and that's a problem. They do the same with wind turbines, but with overhead power cables, birds fly into them. That's a problem. Underground, that obviously reduces that risk. And another one is that severe storms can damage the overhead cables, whereas if they're underground, the storms are less likely, to damage them. Alright, and that is the end of question 1. So let's have a look now at question 2. So it says, in this question you'll be assessed on your use of English, which means we have to write in sentences. I'm going to write in bullet points just so we get the points, but you will have to write in sentences if you see this in the exam. So the information in the box is about the properties of solids and gases. Solids have a fixed shape and are difficult to compress or to squash. Yep, we knew that. Gases will spread and fill the entire container that they're in, and they are easy to compress and squash. It asks us to use knowledge of the kinetic theory, and whenever we see kinetic theory, that basically means we're going to describe what the particles are doing to explain the information given in the box. You should consider the spacing between the particles, the movement of individual particles, and the forces between particles. Alright, so I'm going to start off with solids. I'm going to use a separate colour for the solids and for the gases. So, red for solids. Now, the first thing that we know about solids is that the particles are all really close together. That's why they have a fixed shape. Okay, so particles are very close together. Okay, there we're talking about the spacing between the particles. This actually makes it difficult to compress because the particles actually can't get that much closer together. If we try and push particles even closer together, they're going to start to repel each other. That's because all atoms have electrons on the outside, and so they start repelling. Okay, so particles repel if force tries to move them closer together. There we go. Now, because the particles are so close together, and this is when we're not trying to force them together, there are strong forces of attraction between the particles. Alright, and it's this balance of forces, okay, the repelling if you try to force particles close, and the attraction of the particles when they are not being forced to be close, which makes the particles be held really strongly in place. So they are not free to move. Particles not free to move as forces are strong. Rather than move, they can only vibrate. Okay, so they vibrate around their position, but they're not actually allowed to move. Alright, so let's now talk about gases. I'm going to write the points about gases in blue. So, the first point, well, if we have a look at the solids, the particles are very close together. In gases, it's the exact opposite. Particles are very far apart. Alright. Right, now we couldn't compress a solid because the particles start to repel each other if they move too close. But in a gas, because you've got so much empty space between them, you can easily compress them. So lots of empty space. So easily compressed. Okay. Now, the fact that the particles are so far apart means that they can't really feel the forces of attraction to each other. So there are very weak forces of attraction between the particles. Alright, you would also get the marks if you said there's no force of attraction, because in some cases they are so far apart that there's no force of attraction, but I'm going to say very weak just to be safe. So they're very weak, which means particles can therefore move and do whatever they want. So particles move randomly in all directions, thus filling the container. Because they can buzz around and do whatever they want in all the directions, if you have a container, they're going to move in every direction and fill that container. So that is why they fill the container. Now that is more than enough points to get you the 6 marks here, as long as you've written in sentences, because there's 1 mark awarded for your quality of English. Okay, let's move on. That's just more empty space. So now we're looking at question 3. Right, so here we're told that figure 1 shows one way that biscuit manufacturers cook large quantities of their biscuits. The uncooked biscuits are placed on a metal moving grid, right? That's on the left of this diagram. Now, the biscuits pass between 2 hot electrical heating elements inside the oven. They are drawn here with squiggly lines. And the biscuits turn brown as they cook, and obviously they come out on the right-hand side. Okie doke, let's have a look. In figure 2, we're shown the 2 control knobs on the oven. Okay, we've got a power control and we've got a speed control of the metal grid, so we can speed it up and slow it down. Now, the first question we're asked for 1 mark is which type of electromagnetic radiation causes or makes the biscuits turn brown. Now, you should know that anything involved in heating, so if there is a hot object, it releases a certain type of electromagnetic radiation. So we're all releasing this. Radiators release even more of it, and that is infrared. So it's going to be infrared radiation, and obviously that is IR. Okay, simple enough for 1 mark. Suggest 2 ways of cooking biscuits in the oven to make them turn browner. So we want to cook them even more. Now, if we think about it, we're going to make them turn browner if we heat it up more. And to heat it up more, we need to supply more energy in a given amount of time, and energy per unit time is power. So the first one I'm going to do is I'm going to say turn the power up, which is power dial to the right, just so I'm clear. Okay, so if I turn this dial this way, then yes, the power is going to go up and they're going to turn more brown. Now, what else? Well, we can control the speed of the metal grid. And if the biscuits come in this way and they zoom through within a couple of seconds and then go out, well, they haven't been in there long enough. They haven't had long enough to cook. So if we slow them down, they are going to be exposed to the infrared for a longer period of time, and they're going to cook better, right? Or they're going to cook more. So what I'm going to say is I'm going to slow down the metal grid. The metal grid. Right, and just in brackets, that is speed dial to the left. So if I turn this way, obviously it makes it slower, and making it slower, sorry, you couldn't see that, could you? If I turn it this way, that way, that will make it go slower, which means that the biscuits are going to be in the oven for longer. Alright, there was one more, and it's a less obvious one. When the biscuits have cooked, if you're not changing any of the settings, you take them out and you put them in again, right? You just put them in again, and obviously that will double the cooking time, and that will make them go brown as well. But that is more than enough for 2 marks. Alright, let's have a look at part C. It says the inside and outside surfaces of the oven are light coloured and shiny. Explain why. Now, the inside and the outside surfaces are obviously doing different things, right? The inside surface of the oven is there and it's facing the biscuits and it wants to cook the biscuits. The outside of the oven is not, and so the reasons are not going to be the same. Alright, now obviously the end goal is to make the oven more efficient, right? If the oven was completely black inside and outside, it would be less efficient. So, how is the inside surface being light coloured and shiny making it more efficient? Well, the inside, okay, what that's what that's doing is it's releasing emitting infrared radiation, which is obviously going to cook the biscuits, right? Now, it doesn't want to absorb it back. It doesn't want it to bounce off the walls and absorb it again, right? So, light coloured and shiny surfaces are very good reflectors. So it's shiny, light surfaces are good reflectors of infrared. Alright, you could also say poor absorber, because that's obviously the opposite of reflecting, right? Absorbing. So good reflectors of infrared means that the infrared is going to go to the biscuits. Alright, how about the outside surface? Well, light and shiny surfaces are also the worst emitters. And if the outside is bad at emitting radiation, it means you're not losing energy. Whereas if it was black and matte, that is the best emitter, and so you'd be emitting lots of heat and lots of energy, which could otherwise be cooking biscuits. So the shiny outside surface is a poor emitter of infrared. Alright, that's 2 points. Now, obviously, in summary, both of the above increase the amount of energy used to cook the biscuits. I could say in brackets here, increase efficiency. Alright, perfect. And then that is perfectly fine for 3 marks on that question. So let's move on. Okay, so question 4. Question 4, it tells us a note was played on an electric keyboard. The frequency of the note was 440 Hertz. That Hz is Hertz. What does a frequency of 440 Hertz mean? Now this is basically saying, what is frequency? When you're talking about waves, frequency is the amount of waves produced per second, or it's the amount of wave crests that go past a point every second. Those two mean the same thing, they're a different way of wording them. So I can say a frequency of 440 Hertz means that 440 waves of sound, right? Let's just make sure that we're saying sound waves. Waves of sound produced in 1 second. Alright, so let's have a look at A part 2. The sound waves produced by the keyboard travel at a speed of 340 meters per second. That's generally the speed of sound. Calculate the wavelength of the note. Now it tells you to have a look in the physics equation sheet to use the correct equation. Now obviously I'd always rather you know these equations off by heart, but you will have the equation sheet in the exam with you. The equation you're looking for is speed is equal to frequency times by wavelength, which is given this symbol lambda. Okay, and we always have to make sure that our frequency is in hertz, right? Not in kilohertz or gigahertz or whatever, sorry. And it is in hertz in this case, right? We've got 440 hertz. So we're going to use this equation. So I'm going to say that the speed, which was 340, right, is equal to the frequency, which was 440, multiplied by the wavelength, which is what we're trying to find out in meters. right? So what we do now is rearrange. Well, if it's wavelength times 440, to get rid of the 440, we need to divide. Okay, opposite of multiply is divide, but we need to do that to both sides. Right, so now I've got that 340 divided by 440 is equal to the wavelength. And if we put that in a calculator, we are going to get 0.77, right, that's a 7, 2727, and so on and so on and so on. Okay, now it asks us for 3 significant figures. And the first significant figure here is the first 7 because it's 0 point. So that's the first one, this is the second one, and this is the third one. Now does this last one round up or down? Well, it's next to a 7, so it rounds up. So to 3 significant figures, it's 0.773. Right, so our answer is 0.773 meters, and that is to 3SF. All right, now let's have a look at part B. Now this is over 2 pages, so bear with me on this. It says, figure 3 shows a microphone connected to a cathode ray oscilloscope, right? And that's how we turn a sound wave into a wave that we can see. So it shows the microphone, connected to that, and it's used to detect the note produced by the keyboard. All right, so let's have a look on the next page because it's going to show us our results. Figure 4 shows the traces. So we have this first one. Okay, you can see that the waves are quite long. The wavelength here is quite long. Remember, the wavelength is the distance between 2 crests. So there, that is the wavelength, right? Which means that the frequency is going to be quite low. And also, by the looks of things, this distance here is very low, right? You probably can't see that. That distance there, which is from the baseline to the crest or to the trough, that's known as the amplitude, and that's quite low as well. All right, those are just some observations to start off with, because figure 5 shows the trace produced by another sound wave, right? You can see the difference here. The amplitude to start off with, that's the most striking, it's definitely bigger. Okay, and you can see that the wavelength is smaller, and the frequency therefore is higher because there are more notes in this given amount of space than there are in this one. All right, so the question asks us, what 2 conclusions should be made about the second wave produced by the keyboard compared with the first wave? Give a reason for each conclusion. Now that's why I was observing those traces in such detail, because the first one was the amplitude. Okay, the amplitude was much higher, and you know that amplitude is directly related to the square of the intensity, which in a sound wave is going to be the volume, right? So the second note is louder than the first, and the reason is the amplitude is greater. All right, next difference. Remember, we talked about the wavelengths and therefore the frequencies. Well, the frequency of figure 5 of the second trace is definitely bigger than the frequency of figure 4 because the wavelength is shorter, right? So the conclusion is going to be, oh, hang on. There we are. Well, the conclusion is going to be, well, what is the frequency related to in terms of sound? Remember, a higher frequency means a higher pitch. So the second wave, or the second note, has a higher pitch than the first. All right, and the reason is higher frequency in the second note. I'm going to put in brackets here, shorter lambda, which is wavelength. All right, so that's definitely worth the 4 marks. So let's move on to question 5. Right, so let's have a read of question 5. It tells us Iceland is a country that generates nearly all of its electricity from renewable sources. Right, that's good. In 2013, about 80% of Iceland's electricity was generated using hydroelectric power stations, or HEP. Describe how electricity is generated, in a hydroelectric power station. Include the useful energy transfers taking place. Now, this is really important. A lot of people will sort of just glance over this question and ignore that, right? This is really important, so these are going to gain you marks. When we say useful energy transfers, it means what does the energy start off as and what is it going to end up as, right? Because we have lots of different types of energy and we want electrical energy at the end. But obviously in water, it doesn't start off as electrical energy. It might be chemical energy, it might be elastic potential energy, who knows? So that's what we're talking about when we're saying energy transfers. Alright, so you should know that a hydroelectric power station is one which involves the movement of water. Alright, so this is one where you're going to see dams, right? So you're going to have a large body of water, you allow it to move using gravity, and that movement of water is what is going to drive the generation of electricity. Right, so our first point on how a hydroelectric power station works is going to be movement of water as a result of gravity. So this is going to be downhill, and gravity is going to make that water move. So that water is going to go from stationary, then you allow it to move and it's going to speed up. Right? Now, what are the useful energy transfers there? Well, if we're using gravity, we are saying that at the start we have a high gravitational potential energy. So gravitational potential energy is being converted into, now what's the energy involved with movement? Well, that is kinetic energy. Alright, what then happens? Well, when the water's moving, the water turns a turbine, right? So water, which is moving, will turn a turbine and then turn, I'm going to put in brackets here, or drive the generator, because the generator is where we're going to actually make our electricity. Alright, now what energy transfers are happening there then? Well, kinetic energy of the water is being transferred to kinetic energy of the turbine. So it's going to be, I'm going to use KE for short, so kinetic energy of water to KE of turbine. Right, and that's also going to be transferred to kinetic energy of generator. But you'll notice there are no energy transfers in terms of the type of energy here. So kinetic energy is then converted to electrical energy by the generator. Alright, now that is 4 marks because we've got 2 points describing the ways of which the hydroelectric power station works, and we've also described the energy transfers at each one. So gravitational potential to kinetic, and then kinetic obviously transfers to kinetic, but it is kinetic energy in total being transferred then to electrical energy. And that is enough for part A. So let's move on to part B. Now part B says the UK produces most of its electricity from fossil fuels. Many people in the UK leave their televisions in standby mode when not in use instead of switching them off. It is better for the environment if people switch off their televisions instead of leaving them in standby mode. Explain why. Now this is one of those questions where it seems a bit too obvious for 3 marks, right? You actually have to explain why leaving the television on standby mode affects the environment, not just that it's using electricity, right? That is the first and most obvious point. So TV in standby mode uses electricity. There we go. That's 1 point. That's literally worth 1 mark. Seems crazy, right? Second part. Now, we are told that the UK produces most of its electricity from fossil fuels, right? Now, so we have to say that electricity is being produced by fossil fuels. Right, that's the second point. But that hasn't explained why it's bad for the environment. That is the next step in explaining why. But why are fossil fuels bad for the environment? Well, fossil fuels produce CO2, which is a greenhouse gas. Sorry about the handwriting. And contributes to global warming. Alright, so it seems like a bit of a strange question. A lot of people will look at that and say, well, the TV's using electricity, full stop. But yeah, that's 1 mark, but you haven't actually explained why that's bad for the environment. And this is what it's asking here when it says explain why. Okay. Right, there are a few other answers you could have used as well, because CO2 is not the only thing which is damaging. For example, a lot of fossil fuels have impurities in them, and they can end up releasing sulfur dioxide, and we can also get nitrogen oxides released as well. And you could have used those instead of CO2. CO2 is the obvious one, and that's why I used it. All right, 5C. A scientist wrote in a newspaper that appliances that do not automatically switch off when they are not being used should be banned. Suggest why scientists alone cannot make the decision to ban these appliances. Now, this is also a strange question, because it's quite obvious that scientists do not run the country. Scientists do not create the law, right? So scientists alone cannot make the decision, because there are a lot of legal requirements before any sort of law can be enforced, right? So scientists alone do not have the power to change the law. So that's an obvious point, but that's worth a mark. You could have also given other reasons, like the fact that the economics of it means that all appliances at the moment which don't automatically switch off will have to be banned, and you'll have to replace them. And this is going to cost a crazy amount of money, right? So there are loads of different ways that you could answer this question. It's only a 1 mark question, and so I'm going to leave it at that. So let's move on to question 6. Right, so here we're told that Figure 6 shows a freezer with a freezer compartment. The temperature of the air inside the freezer compartment is -5 degrees Celsius. Now, most freezers are actually colder than that, but let's carry on. The air inside the fridge forms a convection current when the fridge door is closed. Explain why. Alright, now this is a 4 mark question. Alright, so let's have a think about this. You should know how convection currents work. Now have a look at the freezer compartment. It's at the top, right? Now this is important. So, what happens to the air when the door's closed, obviously, that's surrounding the freezer compartment? Well, what's going to happen is that air near the freezer compartment, I'm just going to write freezer, is cooled. Right, obviously because the freezer compartment is at a low temperature. And when it's cooled, loses energy. Alright? Now, if it loses energy, right, that means that the gas particles are not as far away from each other as when they have a lot of energy, because they're moving slower. So let's just put a bullet point there. Next bullet point. So cool air, as a result of that, is more dense than warmer air. We don't have to explain that in terms of the kinetic theory, but it's because the particles are close together. So it's more dense than the warmer air, right? Right, now this means if the air is more dense, it means it's going to sink. So the cool air sinks. Cool air sinks to the bottom. Right, and this replaces the warmer air. I'm not going to say warm air, I'm going to say warmer air because it's still in a fridge. Right, the warmer air which rises. Alright, now that's basically a convection current. I'm just going to add one more point because it's important to know that this doesn't just happen once. Cycle repeats as cool air warms up and the warmer air is cooled. Alright, so that repeats itself and that is a convection current. Alright, let's move on. So 6b, we're given table 1. It shows information about 4 fridges. Right, a householder concludes that the energy used in 1 year is directly proportional to the volume of the fridge. Explain why her conclusion is not correct. Let's have a look at the table. Well, we have volume here and we have energy used here, right? And what this person has said is that they are directly proportional. Now, I can already see this is going to be quite easy to disprove because if we look at D, we've got the volume in litres and the energy used in 1 year is exactly the same, which means that it's going to be times by 1. You've got a factor of 1, whereas the others are not the same, so we can already say that it's not true. But let's use maths to get us an answer. So what I'm going to say is that fridge A, so using fridge A, right, when something is directly proportional, I'm going to say that the volume is proportional to the energy. And that means I can rewrite that as the volume equals something, K, times the energy. So this is the constant of proportionality. So now let's just sub in the numbers. 250 equals K times 300. So to get K on its own, I do 250 divided by 300 equals K. And that's going to give me an answer of 5/6. Okay, right. So let's have a look if that works for C. So for C, what I'm going to say is that 500 should equal 5/6 times by 630. And if you do that in your calculator, you'll get an answer of 525. Now 525 clearly does not equal 500. Right, so we can say that this is incorrect. So therefore, incorrect. Okay, because once we've worked out the constant of proportionality, it has to be the same all the way through, and it's not. So we can say that therefore they are not directly proportional. All right, let's move on to question C. What, sorry, let's slide back up. There we go. So new fridges are more efficient than fridges made 20 years ago. Right, that's true. Give one advantage and one disadvantage of replacing an old fridge with a new fridge. Ignore the cost of buying the new fridge. Right, so the advantages, there are clearly lots of advantages. The most obvious one is costs less to run the new fridge. Right, over time that's going to save you money, so that is a clear advantage. Now the disadvantages, remember, we can't talk about the cost of buying the new fridge. Right? Because that's a clear disadvantage. We've got to go and buy one, but we're not going to talk about that. Why else is it a disadvantage? Well, if you buy a new fridge to replace an old one, well, you've got to throw the old one out, right? And so one disadvantage is disposal of old fridge in landfill. Right? You've got to take it down the dump because it's too big to just put in your bin, I'm assuming. So you've got to take it down the dump, put it in landfill, and that's obviously not a good thing, right? You can also talk about the energy waste in production of that old fridge because it's not being used anymore, so you can say that that's waste energy now. So the fact that you've had to use energy to produce the new fridge and the old fridge is a waste, because if you'd have had the more efficient fridge to start with, then you wouldn't have had to do that. Right, so there are a few avenues you can go down. This is the most obvious one, the fact that you have to get rid of the old one. Right, that's going to cost you money, and it's also damaging to the environment. All right, so let's move on. So let's have a look now at question 7. Well, here we are told a student uses the apparatus in figure 7 to obtain data needed to calculate the specific heat capacity of copper. Right, so we've got a power supply, we've got a joule meter. Obviously joules is going to mean energy, so it's going to measure energy. And we have our copper block, right, which is this dark part. And you have an immersion heater. And we have a thermometer. All right then. So the initial temperature of the copper block was measured. The power supply was switched on. The energy transferred by the heater to the block was measured, obviously using the joule meter, as we said. The temperature of the block was recorded every minute. The temperature increase was then calculated. Figure 8, so this graph here shows the results. And so this is pretty good, but you can see that it's curved, right? We should know that specific heat capacity tells us that it should be a straight line, but this is actually a curve, so that immediately suggests to me that there's a slight problem in this experiment. Right, but let's have a look at the next page, and we'll have a go at the questions. So part A, energy is transferred through the copper block. What is the name of the process by which the energy is transferred? Now we've got 3 choices: conduction, convection, or radiation. You should know straight away that it is conduction, right? Convection happens in fluids. A copper block is not a fluid. We've already looked at convection currents earlier on with the fridge, and so it's not that one. Radiation is when energy is emitted, okay? It's given out from something, not traveling through that something. When energy travels through, it is conduction. Right, question B. Figure 8 to determine how much energy was needed to increase the temperature of the copper block by 35 degrees Celsius. Right, let's go back and we'll have a look at this graph. So, increasing the temperature by 35 degrees, well, we start at 0 here, okay, and let me use a different color. So 0 is there, and 35 degrees is here. So let's read across, okay, let's make this as straight as possible. We'll read across, there we go, and this here is the 35 degree mark. And now let's read down to see how much energy that is. That is bang there, and that is halfway between 30,000 and 40,000, so that's going to be 35,000 joules. So let's go back, and we're just going to say 35,000, and they've given us the units joules. Okay, that's only 1 mark, that's fine. 7C. The mass of the copper block is 2 kilograms. Use the answer to part B to calculate the value given by this experiment for the specific heat capacity of copper. Now for this, we're going to use the correct equation from the equation sheet. I'd rather you know the equations off by heart. Right, you should know that the equation is given by E is equal to M times C times by theta. Right. E stands for energy. So we've got energy is equal to mass, and the mass is in kilograms, times by specific heat capacity, I'm just going to write SHC, times by theta, which is change in, this triangle means change in temperature. Change in temperature. Okay, right. So now let's sub our numbers in. Our energy change, right, or the amount of energy transferred was 35,000 joules. So 35,000 is our E. And that is equal to the mass in kilograms, which is 2, times by C, which we don't know, we're trying to work out, times by the change in temperature. And the change in temperature was 35 degrees Celsius, okay? In Kelvin and in Celsius, the temperature is going to be the same thing. The temperature change, sorry, is going to be the same thing. All right, so let's just tidy up. Well, 35 times 2, that's going to make 70. So I'm going to say 70, lots of C is equal to 35,000. Now to get C on its own, I'm going to divide both sides by 70. Right, and so I'll get 35,000. Oh, let's write a bit bigger. Divided by 70. So 35,000 divided by 70 equals C, right? And that is going to equal 500. All right, so we get 500. Now that is our answer, 500. It's also asked us to give the unit. Well, let's have a think. What we've done is we've divided, let me rub this out to make room. What we've done is we have divided energy by mass and by temperature, right? Theta. If I sub in the units, that is joules divided by kilograms, which is also times by temperature, which is going to be degrees Celsius, right? And so that is going to give me a unit of joules over kilograms degrees Celsius. And it's as easy as that. You don't have to just remember the units, you can just work the units out given what you've done in the equation, right? Joules over kilogram degrees Celsius is your answer for your units. And now lastly, let's have a look at 7D. The experiment does not give the correct value. So remember I said that graph was curved, so this is confirming that. It doesn't give the correct value. Suggest one reason why. Well, if you remember back to our first part, right, we said that conduction was how the energy goes through the block. We also said that radiation is when energy is given out, right? That is a key here. A block is not going to be absolutely perfect at just keeping the energy, because remember, we're doing this over time. Energy is going to be released. So I'm going to say that energy has been lost or released into the environment or surroundings. Okay, so that tells us that not all of the energy has been measured here. Some of it has been lost, and that will affect our results. All right, and that is perfectly fine for question 7. So finally, let's move on. All right, so now let's take a look at question 8, which is the final question on this paper. So we're given table 2, and it shows us information about different light bulbs. The bulbs all have the same brightness. So we're given a halogen bulb, a compact fluorescent or CFL, and an LED bulb. And we've got the power input, and we've got the efficiency of those bulbs. All right, it asks us to calculate the useful power output of the CFL bulb. Right, it asks us to use the equation from the physics equation sheet. As usual, I would rather you remember these off by heart, but you can use the equation sheet if you need to. Right, so we know that efficiency, right, efficiency is equal to the useful output, right? So I'm going to say useful output divided by total input. All right, and if we want percentage efficiency, then you just times that by 100. But in this case, we're not using percentages, we're just using decimals. All right, so if we sub in some numbers, we have for our CFL bulb, the efficiency is 0.42, and that is equal to output, which is what we're trying to find. Right, so I'm just going to say O for output, and that's O, and that's divided by total input, and our input was 14 watts. Okay, right. So to rearrange, we need, because we're dividing on this right hand side by 14, we need to times by 14. So we multiply by 14 to get rid of it, and we must do that obviously to both sides. So we're going to end up, let's write down here, we're going to end up with 0.42 multiplied by 14 equals our output, which is O, right? I'm just going to put output there so you don't think it's 0, which is equal to, if you do that in your calculator, you'll get 5.88, and that's obviously going to be in watts. So we have 5.88 watts as our answer. If you'd rounded that to 5.9, then you would still get the marks, right? Okie doke, second part. So use your answer to part 1 of A to calculate the waste energy produced each second by a CFL bulb. Right, now the wording here is made to confuse you, but just remember that 1 watt equals 1 joule per second, and it's asked us each second. So this is going to be pretty easy. right? All we're going to need to do is work out, well, how much of our power is waste, because power is equal to joules per second. So if we are producing 5.88 watts of useful power out of 14 watts input, all we're going to do is we're going to say, well, 14, which is our total input, minus our useful power, okay, which is 5.88, is going to give us our useless. So, yep, so our waste energy, or our waste power, sorry, in this case. So we take those away, put that in your calculator, and you're going to get 8.12 watts, right? And so if I come down back here and I say 8.12 watts, well, that is equal to 8.12 joules every second. And it asks us the waste produced each second. So that's just going to be 8.12 joules, right? That's why this is a 1 mark question, but the wording is going to throw some people off. All right, so let's move on. So now we've got 8b. A growth cabinet is used to investigate the effect of light on the rate of growth of plants, right? It sounds like biology, but we promise it's not going to be. So in the cabinet, the factors that affect growth can be controlled. A cooler unit is used to keep the temperature in the cabinet constant. The cooler unit is programmed to operate when the temperature rises above 20 degrees Celsius, right? So when the temperature goes above 20 degrees Celsius, the cooler is going to kick in. The growth cabinet is lit using 50 halogen bulbs. Changing from halogen bulbs to LED bulbs would reduce the cost of running the growth cabinet. Explain why. Right, now this might seem obvious first of all, but let's take notice here that this is worth 4 marks, right? So there's got to be something slightly more complicated going on as well. Obviously, if we go back to our table on the last page, we can see that LEDs, right, because this is what we're comparing LEDs and halogens, right? The LEDs use way less power than the halogens, but both bulbs have the same brightness. And remember, it's the amount of light that plants need, not the temperature. So if they are the same brightness, then it means we're going to reduce our amount of input power, which of course is going to save us money. One thing you also want to see is that we have an efficiency of 0.85, whereas halogens have an efficiency of 0.15, right? So way less waste is going to be produced. Now this is very important. So let's go back, and my first point is going to be that less input power required for the same brightness equals lower energy cost. Okay, so that's the obvious point. The second point is efficiency is greater, so less waste energy. All right. Now, I don't know if any of you have halogen bulbs at home. I'd imagine that you probably do somewhere. Have you ever felt a halogen bulb after it's been on for a long time? Well, I hope not, because it's scorching hot. It gets very hot, and that's because it's only 0.15 efficient, according to this table anyway. They're not very efficient because lots of the energy is heat, not light. So they give out a lot of heat energy, and that's the waste, and that's important here. So less heat will be given out by the LED bulbs. Okay. And so think about the link here. It says that a cooling unit kicks in when the temperature rises above 20 degrees Celsius. Well, if loads of heat is being given out by halogen bulbs, the cooling unit's going to have to do its job more often because the temperature is going to be going up. So what I'm going to say is less heat will be given out by the LED bulbs. So the cabinet temperature will not increase as much. Okay, and so the fourth part, well, the cooling unit is clearly going to require energy. So the cooling unit it's clearly going to be needed less often, which saves energy. All right, so that is 4 points. And that's why I said that this question is actually a little more tricky than it first sounds. At first glance, it's like, well, yeah, it's obvious that LED bulbs are more efficient than halogen bulbs, so it's going to save some cost, right? But because we've got that extra detail of the cooling unit, well, the halogen bulbs are going to mean that the cooling unit is needed more often as well. So the LED bulbs are going to save even more energy on the cooling unit. Okay, so I hope you could follow that. Let's move on. Right, so B part 2. Scientists measured the rate of growth of plants for different intensities of light. What type of graph should be drawn to present the results? Well, if we think about it, the rate of growth of plants and light intensities, well, both of those are continuous variables. And by continuous, it means they don't take a discrete number. So, for example, if I said number of fingers, that's 1, 2, 3, 4, or 5. And even more, if you've got polydactyly, it might be 6, might be 7. But you can't have 5 1/4, you can't have 5.327, right? You have a finger or you don't. Whereas light intensity can be any number and it can be any decimal. Same with the rate of growth of plants. So both are continuous, and when that happens, we need a line graph. All right, because a bar graph is going to be when you have discrete variables. Okay, so that will be what I write for the reason. Both variables are continuous. We go continuous. All right. Okay, so moving on. 8C. Table 3 gives further information about a halogen bulb and an LED bulb. A householder needs to replace a broken halogen bulb. Compare the cost efficiency of buying and using halogen bulbs rather than an LED bulb over a time span of 48,000 hours of use. Your comparison must include calculations. All right, perfect. So we have a time frame. All right. This is a 4-mark question. Let's have a quick look at the table. Well, first of all, we're given a cost to buy. Right, that's important because that's going to be the upfront. Do I buy a halogen bulb? Do I buy an LED bulb? Right. We then have the lifetime in hours. Okay. 48,000 for an LED, only 2,000 for a halogen. And we then have the operating cost over the lifetime of one bulb. Okay, 16 for a halogen and £67.20 for an LED. Now I'm going to do the halogen and LED calculations in separate colours so you can see exactly what I'm doing. But let's start off with the cost in total of halogen bulb over 48,000 hours of use. All right. So halogens are going to be in purple. I'll just write that there so you can see. Now the first thing which is going to catch people out is that we are not comparing one halogen bulb to one LED bulb in this case, because it asks us for a time span of 48,000 hours, but a halogen bulb only lasts 2,000 hours. So how many halogen bulbs are we going to need over that 48,000 hour usage time? Well, it's going to be that 48,000 divided by how long does a bulb last? 2,000. Well, what is that going to give us? That's going to give us 24. We're going to need 24 halogen bulbs. So what that means, right, I'll just write bulbs there. We need 24 halogen bulbs. So in total, the cost is going to be the upfront cost of not one bulb, but 24 bulbs. So it's going to be 24 multiplied by, well, how much does one cost? £1.50. Now that is going to give me a grand total of £36 up front, and that is the total cost of buying those bulbs. Now, the operating cost over the lifetime of one bulb. This is important. It says one bulb. We've got 24 bulbs, so we're going to have to multiply this by 24 as well. So it's going to be 24 multiplied by, well, what's the operating cost of each bulb? £16 and no pence in total. And that is going to give us a grand total. I keep saying grand total. I shouldn't really say grand total because that's going to be at the end, right? But that's going to give us a total of, if you do that in your calculator or in your head, it's going to be £384, right? And no pence. So both of these, no pence. So in total, this is the grand total, right? What we're going to do is we're going to add those two together. And if you do that, you're going to get £420. So over the 48,000 hour lifetime usage, you are going to spend £420 on halogen bulbs. So let's now take a look at the LED bulb. So I'm going to do that in a separate color. I'll do that in orange. Alright, now first of all, just like before, how many bulbs do we need? Well, the lifetime of the LED bulb, conveniently enough, is 48,000, right? 48,000 hours, which means how many bulbs do we need? We only need one of them. Perfect. So what we need is we need one lot of £30, and that is our upfront cost for the bulb, which is obviously £30. I'm only writing this so that it looks the same as the halogen calculations. You don't obviously need to write this 1 times if you didn't want to. Then how about the lifetime cost of a bulb? Well, the lifetime cost of the bulb to run it is £67.20. So it's going to be one lot of that, one lot of £67.20. And that's going to give me £67.20. We then add those two together and we get a grand total of £97.20. So that's 3 out of 4 marks, and now we just have to write a final statement. Okay, I'm just going to put it on the same page, but you could have done it anywhere else in the paper when they give you extra lines. But over the course of 48,000 hours, we can clearly see that the LED is way cheaper than the halogen. So I'm going to say LED cheaper than halogen. Okay, and I can say how much cheaper as well if I want to. I could say that 420 minus 97.20. Let's put the pounds in there. Gives me a saving, if you do that in your calculator, of £322.80 saving. Alright, and then that would finish off that question. And that is the end of the entire paper. So I hope you've been able to follow. Obviously, if I was going too quick, please do feel free to rewind and just rewatch as you like until you'll understand. But I hope you've enjoyed that. I hope that has helped. If you do have any questions, though, regarding anything we went through, please do feel free to send me a direct email using the box below, or post a comment and I'll be sure to get back to you. But as usual, please do like and subscribe, as there are plenty more videos coming up very soon. But I look forward to seeing you in the next one.